Hey guys, in this video I'm going to talk you through 2014 number 4. This is a no calculator problem, so just know that. And it talks about a train. It's running back and forth on an east-west railroad track. It says train A's velocity measured in meters per minute is given by a differentiable function v sub a of t, where t is in minutes, and it says selected values for that function is given in the table. So we have a bunch of velocities for train A here. Something to point out, when they mention that it's a differentiable function, remember that means that you automatically know it's a continuous function. If something's differentiable, you can find the derivative, you know the function is continuous. So I might just write that v sub a of t is continuous. That might help us if we have to use that intermediate value theorem. For intermediate value theorem, the function has to be continuous. So that's good that they tell us that. But let's take a look at part A. It says find the average acceleration of train A over the interval 2 to 8. All right, so if we're going to find average acceleration, there's that formula for average value of a function. Remember that formula was 1 over b minus a integral a to b. And if it's average acceleration, I'm going to put the name of that function, acceleration, there. We don't have that function, right? We have velocity. We'll figure that out later, but we need to put the right function in there. All right, and it looks like our 2 is going to be our a, our 8 is going to be our b. So if we plug those in, 1 over 8 minus 2, integral 2 to 8 of a of t dt. All right, and if we simplify that a little bit, 8 minus 2 is 6, so that's 1/6. And then what do we do over here? You know, if they actually gave us a formula for acceleration, maybe we could take the antiderivative there. We really can't do that. But let's try to think backwards. You guys know the antiderivative of acceleration is velocity. So if we were kind of thinking along those lines of taking the antiderivative, if we just kind of write this in symbols, the antiderivative of acceleration is velocity, and we'd be evaluating that from t equals 2 to t equals 8. And we're talking about of train A, so velocity of train A, we have, I could put a little a right here, this is that table we have. So if we plug in 8 and we plug in 2, we'd have 1/6 of v sub a of 8 minus v sub a of 2. And I think those are actually values in our table. We got 2, we got 8, we can plug those in. All right, if we do, we get 1/6. V of 8 is negative 120. V of 2 is 100. And you have to do this without a calculator, so that's negative 220. We get 1/6 times negative 220. So you can't see that. All right. And if you simplify that, you could probably call it negative 110 over 3 would probably be the best answer. All right. They don't ask for units, I don't think, so I would not include them. I would just call that the answer. All right. All it was that average value formula. All right, let's look at part B. It says, do the data in the table support the conclusion that train A's velocity is negative 100 meters per minute at some t on 5 to 8? So train A's velocity. We have a bunch of velocities here. They're talking on 5 to 8. If we locate that interval, this is the interval 5 to 8. At a time of 5, the velocity is 40. At a time of 8 is negative 120. We need to ask ourselves, is negative 100 in between 40 and negative 120? And it is, right? Probably easier to think about the interval negative 120 to 40. But if you went from negative 120 up to 40, you would have to pass negative 100. All right, so the answer would be yes. It's going to be that intermediate value theorem. So remember, for intermediate value theorem, you just have to mention the 2 points, 5, 40, 8, negative 120. You have to mention that the function is continuous, and that's basically it. So I'm going to say for part B, the answer is yes, and say since v sub a of 5 is equal to 40, that's that first point. This interval was 5 to 8. V sub a of 8 equals negative 120. That's our second point. And V sub A of t is continuous. We knew that from right there. It's continuous on that interval 5 to 8, right? That's what they're asking about. Continuous on 5 to 8. And then we really just have to kind of say what the problem is saying. Since all this is true, train A's velocity is negative 100 meters per minute at some t on 5 to 8. And I might just say by the intermediate value theorem. You should mention that. Right? Key components in that. You got to mention both points. You got to mention the function is continuous. And from there, really all I did was state exactly what the problem said. I copied it exactly there and said by the intermediate value theorem, we know that's true. All right, hopefully not too tricky. Let's look at part C. There's a lot of writing there. Let's go step by step. It says at a time of 2, train A's position is 300 meters east of origin station. When we talk about position, I know this problem already mentioned acceleration. It has a table of velocity. If we think about position, we used to use that function s of t for position. So I might just write down right here, we know that s of 2 equals 300. I'm going to call it positive 300 because east on a map is to the right. I think it would be positive 300. So that's for train A. That's the position. And it says the train is moving to the east. It says, write an expression involving an integral that gives the position of train A in meters from the origin station at a time of 12. So we want the position of the train at t equals 12. We want s of 12. All right, I'd be thinking if you're given one point, you want another. That's usually fundamental theorem of calculus that we're going to use. You might even want to write yourself a note. Typically, fundamental theorem of calculus looks like this. Integral a to b of f prime of x dx equals f of b minus f of a. These are the points on the original graph. So if we want s of 12, we have s of 2. I almost think our problem, definitely our bounds should go from 2 to 12, right? From 2 to 12. Over here, we want it to be s of 12 minus s of 2. That's our setup. We need to think what function would go here. If we kind of look at the formula, this is f. Its derivative is over here. The derivative of position is velocity. So I will put the velocity of train A over here, which is what our table gives us. All right, so that's kind of what we got to figure out. We don't know s of 12. We do know s of 2. We got to figure this out, and I think the directions give us a hint on that. They say use a trapezoidal sum with 3 sub-intervals indicated by the table to approximate the position at t equals 12. I think they're saying that we need to use a trapezoidal sum here. And be careful, it's from 2 to 12. So in our table, we have 0, 0. We're going to ignore that. We're only doing from 2 to 12, and they want a trapezoidal sum with 3 sub-intervals. So I think this is 1, 2, 3. 1, 2, 3. We need a trapezoidal sum there. I might just cross this out for a second. We're not going to use this in the trapezoidal sum. All right? And think about a trapezoidal sum. We have to do the left Riemann sum plus the right Riemann sum divided by 2. So I think that's how we're going to find this. So I might start working on that right now. All right? I might just kind of move this up. This is some stuff we know right now. But just a side note, we need to do the left Riemann sum and the right Riemann sum here. So if we start setting it up, the first box is 3 units wide. The next box from 5 to 8 is 3 units wide. And the last box from 8 to 12 is 4 units wide. We could probably set up our right Riemann sum at the same time. The boxes are the same width. All right. Now we got to pick our numbers for the left Riemann sum. These numbers right here, we're picking the numbers on the left side of each box. So 100, 40, and negative 120. All right, and the right Riemann sum, we're picking the numbers on the right, 40, negative 120, negative 150. All right, and we have to actually do this without a calculator. This is a no calculator problem. So let's think about this. 3 times 100 is 300 plus, I'll go 3 times 4 is 12. So that's 120 minus 4 times 12 is 48. That's minus 480. All right, if we add these together, 300 plus 120, that's 420 minus 480, which looks like negative 60. Is our left Riemann sum. We need to do our right Riemann sum too. 3 times 4 is 12. That's 120 minus 3 times 12 is 36. So that's negative 360 minus 4 times 15 is 60. So I think that's negative 600. If we add that together, that's 120 minus 960. If we add that up, that's negative 840, I believe. Yeah, that looks right. So those are our left and right Riemann sums, but remember they told us the directions told us to use a trapezoidal sum. So for a trapezoidal sum, we said it's the left Riemann sum plus the right Riemann sum divided by 2. So we just found those. Our left was negative 60, our right is negative 840. We got to divide by 2. If we get that, we get negative 900 divided by 2, or negative 450, is our trapezoidal Riemann sum. So that should actually help us. We said this was kind of the setup of our problem. The whole goal was to find S of 12. We know S of 2, and they said for this, they gave us a hint that we should use a trapezoidal sum. So that's going to be our negative 450. So if we kind of copy that problem again, I'm going to take that problem down here. It was 2 to 12 v sub a of t dt equals s of 12 minus s of 2. All that was fundamental theorem of calculus, and we're going to plug in what we know. We found negative 450 for our trapezoidal sum. That's estimating that area under the curve from 2 to 12. S of 12 is what we're looking for, and S of 2 is 300. And if we just add the 300 to the other side, all right, we end up with negative 150 equals S of 12. All right, and I believe that is our answer. The question, if I pull that up, our question here was use that trapezoidal Riemann sum to find the position of the train at t equals 12. You probably could explain that if you want. We got a negative position, so think about that. What that means, it's in relation to origin station. Negative 150, it said the train was traveling east and west. That would mean 150, I think we're talking about meters, 150 meters west of origin station is where that train is, if you wanted to explain it or make sense of it. This answer would probably be good enough since the question did not ask for an explanation. All right. Last part. We have part D. It says a second train. So they're introducing a whole new train, train B. We haven't heard about this at all. We had no information. It's traveling north from origin station. Okay. It says at a time of t, the velocity of train B is given by this. So we have a table for train A, but we actually have a velocity equation for train B. And then it says at a time of 2, the train is 400 meters north of the station. So that's good to know. Now it says find the rate in meters per minute at which the distance between train A and B is changing at time t equals 2. It's been a while since we've done these problems. This is a related rates problem, and you always drew a diagram with related rates. So I would just draw, they start talking about origin station. Let's say that origin station, I'm going to label it right here with an O, that's going to be origin station. It said that second train, train B, is traveling north, so that would be traveling straight up. So let's say this is train B up here. All right, and then also I think we need to go back and look at, this talks about train A too. So train A They told us about its position. It was east of the origin, and it's moving east. So east is to the right. So train A is going over here. All right, and they're asking about the distance between train A and B, how it's changing. So I think we need to connect this. We need to form a right triangle here. All right, we probably want to label our sides. Usually the horizontal we label X, the vertical we label Y, the hypotenuse we label Z. You could also call it A, B, and C, either way. But if we're looking for which the distance between train A and B, that's Z, how is that changing at time t equals 2? If that length is z, we're looking for dz dt when t equals 2. That's what we're trying to figure out. All right, the formula that relates x, y, and z is Pythagorean theorem, right? A squared plus b squared equals c squared. If we set that up, x squared plus y squared equals z squared. All right, remember to solve this, we need to take the derivative of all of this with respect to t. So the derivative of x squared is 2x, but since there was no t there, you have to put a dx dt there. Plus, derivative of y squared is 2y, you need a dy dt. And over here, 2z dz dt. All right, now we got to figure out some values to plug in. I think they gave us, this is all at time t equals 2. So at time t equals 2, the train is 400 meters north of the station. This is 400. I think they also told us about train A up here. At t equals 2, train A's position is 300 meters east of the station. All right, and think, that's a 3, 4, 5, right? 300, 400. This is 500. All right, remember, you could plug those in for x, y, and z. Remember, you have to take the derivative first, then you can plug them in. You can never plug in anything right away if it's changing. And all these trains are moving. This train is on the move, this train is on the move, this distance between them is changing. So at this point, you could plug those values in for x, y, and z. So for x, we'd get 300. I might leave this blank, I don't know what it is yet. Plus 2 times y was 400. I'm leaving this blank, I don't know what that is yet. Times 2z is 500. And dz dt is what we're finding. So I'm going to leave that right there. We got to figure out the rate at which x is changing with respect to t. If you think about it, x is just the distance that train A is going. If it's the rate at which x is changing, it's really just the derivative. That's going to be the velocity, how fast train A is going. And it's at t equals 2. This is just kind of a different name, but really it's just the velocity of train A at t equals 2. So we could go to that table. We have the velocity of train A at t equals 2. It's 100. All right, so we could plug in 100 there. They just kind of used a different name, dx dt, but that's the rate of change. How fast that train A is going at t equals 2 is 100. And then same thing here, dy dt, just the rate at which y is changing. It's really just the velocity of train B at t equals 2. And remember, we were given this velocity right here. We just have to plug in 2. So if we do that, if we plug in 2, negative 5 times 2 squared plus 60 times 2 plus 25, we should be able to figure that out. 2 squared is 4. 4 times negative 5 is negative 20. 60 times 2 is 120 plus 120, and then plus 25. All right, so think negative 20 plus 120 is 100, plus 25 is 125. The velocity of train B at a time of 2 is 125. That's what we could put in here. All right, and we are basically done. We just have to solve this. And again, you can't use a calculator. So I would just carefully do this. If you think about this, 2 times 3 is 6. And then I might just add the zeros. There's 1, 2, 3, 4 zeros. Plus over here, I might go 2 times 4 is 8. That's 800 times 125 equals 2 times 5 is 10. And add the zeros. And you get dz dt. We're trying to get dz dt by itself, so we could probably divide everything by 1,000 at this point. that might help us out actually a lot to just make these numbers a little bit easier to deal with. So I think those cancel. All right, we get 6 plus over here, these zeros cancel. We get 8 times 125 all over, we still had a 1 and a 0 there, all over 10 equals dz dt. All right, so let's think about that. This might be a little bit tricky, but 8 times 125. I'd be thinking if we just thought of this as 100, 8 times 100 is 800. If we think about 8 times 25, that's 200. If we add those up, that's really 1,000. So we'd get 6. And actually, I think I was missing a 0 up here. 1, 2, 3, 4. We were missing a 0 up here. This should have had 60. Sorry about that. So 60 plus over here, we just said 8 times 125 is 1,000. All over 10 equals dz dt. All right. And from there, cancel one more 0. We got this. 60 plus 100 is 160 equals dz dt. I think that's all we had to find. It just said the rate at which the distance between train A and B is changing. It didn't ask for any units. That's your answer, and you're done. All right, so I know this was a lot of work, but this is why we did this problem together. It's a hard one, but it's really stuff that's doable. You know, all we did was the average value formula in Part A. Part B, we had intermediate value theorem. Part C was a little bit of trapezoidal sum, a little bit of fundamental theorem of calculus. And Part D, related rates. I know it's been a while, but we can handle it. All right, hope you found this video helpful.